All right, so welcome back from lunch, everybody. I hope you got a chance to eat and go outside and rest a little bit. There are just a couple things I wanted to bring up before we start our presentation from Rich. So the afternoon, the only lecture this afternoon is by Rich on atmospheric parameterizations, and then we're gonna have more time for the lab exercises. So before you run away, we're gonna check in with you. We wanna kind of break up the groups a little bit more based on how far along you got so that we can get people help where we need help. So don't just run away, but we'll kind of direct you to different breakout rooms after Rich's talk is done. And then there will be a break just in the middle of the lab. I just wanted to point this out from 2:45 to 3. There will be food out here in the lobby. So you take the break on your own time in the middle of the lab exercises, and then we'll come back here at 4:30 to kind of have a debrief. Okay. The other thing I just wanted to point out, I did try to send this to everybody. I'm not sure if people got it, but I've assigned people to the Meet a Scientist lunch and the Mesa Lab tours. So you should look at this spreadsheet and just, you can search for your name. And if you're Olivia, wherever Olivia is, you can see I've assigned you to be with Betty in the Chapman room tomorrow at lunch. You can search for whoever you are. These spots here are open availability if you want to try to meet with someone and you're not on here already, but we do only want you to meet with one person because we just don't have space for everyone to meet with more than one person. And then if you wanted to do a tour, I've signed people up here so you can look for your name here as well. And there are some spots on Wednesday or Thursday. So again, if you're interested, please come tell me. I've closed that form that you could fill out before arriving. So you'll have to actually just come tell me if that's what you want. All right, so I'm gonna go ahead and introduce our next speaker. This is Rich Neal. He'll be up here in a second. He does atmospheric model development here. He's worked a lot with CAM, and he studies the tropical Pacific variability, general tropical things and convection. And he was the atmospheric model working group co-chair for a long time, but he is not anymore. So without further ado, here's Rich.
All right. Thanks a lot, Alice. Presume I'm good on the microphone up there. Yes, maybe. So, yeah, I mean, the first thought is 30 minutes to talk about atmospheric model development over many, many, many years. I've been doing it 20 years, so, it's your life work in 30 minutes to a certain extent. And not just your life work, many other people's life work over 20 years. So, it was brutally hard to put this into 30 minutes. I've put a lot of slides at the end. I'll tell you in advance that talk about process interaction, so please consult those if you're interested. So in terms of the outline, I'd like to talk a little bit, not necessarily just parameterizations. I think it's talking about the physics of the problem as well as the parameterizations. I'll say a little bit about how we distinguish GCMs from other models, in particular time and space scales. And that kind of drives on drives the process of how we do parameterization of subgrid processes. And so, no surprise, representations in the atmospheric model in CAM relate to condensation, clouds, microphysics, radiation, how that interacts with the condensation, clouds, and microphysics. And then also a boundary layer representation, surface fluxes, gravity waves. I'll probably cut some of these a bit short. And ultimately, where we are now in a more unified methodology for this. And like I said, I like the process interactions, but it makes the talk 3 hours. So, and there's a little bit about model sensitivity and future parameterization. So, where do we sit as a GCM, and what are we trying to do? So this is, along the x-axis is spatial scale, a meter to 1,000, 10,000 kilometers, the globe essentially. Then 1 second up to 1 week. And so essentially, put it on here, climate models occupy this somewhat small space in terms of what are they trying to resolve, at least in this temporal spatial diagram. And so, yeah, exactly. We're in the realm of, above maybe 50 to 200 kilometers, and then around, an hour or so, hours to days of the resolve scale. So we do not occupy these spaces of these more finer scale, shorter time scale models. And so that dictates the scales, essentially, what we're interested in and what we have to parameterize. And I'll tell you what I mean by parameterize in a sec. And so this is just a gross example in terms of a cloud field in the South Atlantic, South Pacific somewhere, maybe South Atlantic. And then, basically you can see, this is of order 100 kilometer squared box, which we have, in the model, we have one value of everything, of quantities at every level. That's it. That's all we've got. That's all we can predict, ostensibly. But of course, there's a whole rich variety of activity here, and that is subgrid scale in nature and important from condensation to radiation to precipitation perspectives. And this is just a kind of a cloud wake. There's an island there, I think Selkirk Island, yeah. And then, you just see what happens in terms of spatial scales. That's in cloud, and you can imagine radiation more close to home, especially this summer, if people are in this region. This is, back in 2015, and there's the states there, Midwest. And so we have these, pretty impactful storms that are, going through these regions in the afternoon in spring and summertime. And we can see that, the focused activity, again, that yellow box is 100 kilometer square grid box, I think. And we can see that, very important pinprick precipitation. It does not occupy the whole grid box, and it's very intense in a particular region. And, we need to think about, given the restrictions that we have, which is of order 50 to 100 kilometers squared kind of resolved scales, how do we represent that? And so moving through our process, clouds. We spend vast amount of our time trying to understand why clouds occur where they occur, how they interact with other processes. They keep people awake at night, essentially, in terms of thinking about how, fiendishly hard it is to represent them. And of course, I don't need to tell you these types of clouds, they look challenging to represent, given the caveat, again, we have 100 kilometer squared boxes. So, I'm going to go through, some of the processes that we've kind of represented in previous versions of the models and current, just to kind of illustrate how we would implement the physics we want to represent, and how we represent that with respect to the scales we have to deal with in the model. And for clouds, it's kind of, we tend to separate out, kind of historically, and kind of by process, we tend to separate out into what we call large-scale clouds that can be, in some sense, more easily diagnosed at the grid box level, but also these smaller scales that we saw in the previous example, shallow and deep convection clouds. They have different characteristics we try to exploit. Did I miss something? Oh, did I jump that? I didn't. I jumped this. I didn't realize I jumped this. I apologize. So this is, I wanted to say specifically what I mean and what most people mean by parameterization. So it's to represent the impact of subgrid scale, unresolved processes that I showed on those big grid box examples on resolved scale, essentially, with the large scale dynamics that Peter talked about. They're usually based on things consistent thermodynamic laws of conservation that we can exploit. We know, exist on many scales. If we don't have that, we rely on empirical formulations. One example is trying to relate ice habit characteristics to the mean ice content. That's not a conservation we're trying to exploit. That's just empirical. We look at aircraft observations and we figure out relationships that we exploit. And just basically to reiterate that here. And one of the simplest examples I always like to show, I think it's illuminating, is, vertical eddy transport of some quantity, some gas, some aerosol, some conserved, theta, temperature, base variable. And we want to, W prime W is the vertical velocity, and they're eddy covariance. So essentially saying, what is the upward vertical velocity? And if that's covarying with a particular quantity, you transport it. And we can see the way that it's still done in models, essentially, as you say, is related to the mean gradient in the vertical, which we know. It's a resolved thing, d chi by dz. And there's some efficiency factor, which is in a diffusivity. So that's just a very basic example of relating a subgrid scale quantity to a resolved quantity. And that's what we're trying to exploit. All right, and now skip to go back on to the rails. We were thinking about cloud, and resolved cloud is the first cloud type. And this is just an example of, liquid clouds, when relative humidity is greater than 100%, you form clouds. Yeah, of course. But we need to know how that occurs in a huge box where sometimes it's above 100 100% relative humidity, sometimes it's 50%. But on average, you get an average value. And so then you have to say, well, you're trying to formulate and say above some average value in a grid box, we call RH crit, cloud starts to form, because you think in some regions it is above 100%, and you take this from observations, again, a kind of empirical relationship. And so basically, I shouldn't touch this yet, as you go from this relative humidity, this critical relative humidity, and we have essentially the cloud fraction, it varies between there and 100%. If your mean is 100%, then yeah, you say it's 100% everywhere, so I have cloud everywhere. The devil in the detail of a parameterization is, how does that blue line vary? Is it linear? Does it start off pretty low? And vice versa. And so the devil in the detail of parameterization, as an example, is in the formulation of that blue curve for cloud fraction. The other two types, shallow and deep. So they exploit essentially conservation properties, thermodynamic conservation properties. For shallow convection, it tends to initially be unsaturated, and we know that vertical displacements of air follow kind of dry static energy, constant theta, potential temperature properties in the vertical when we displace air particles. So we exploit that, and we exploit values of buoyancy. Shallow convection is cooling mainly. It's a force phenomenon. It's being forced by kinetic energy from the boundary layer, turbulent kinetic energy, and condensation. It's generally a source of water vapor, so it injects water vapor in the air. It doesn't rain that much, and so it then tends not to be a sink of water vapor. And these tend to be small clouds, so we see here, and so they have a strong entrainment. They tend to be suppressed by aspects of the large-scale humidity field. Deep is different in terms of they go from, as I said, hundreds of meters through to tens of kilometers. It's non-local in the vertical. Obviously, they penetrate a lot in the vertical through to as you look out the window, I'm sure, well, maybe not this week. You should have been here last week. Look out the window, you see deep clouds forming. And they're slightly different. So they take advantage of the fact that moist static energy is conserved there. So they saturate, and then they warm the atmosphere, and then they're able to become very buoyant. And then because these clouds are much larger, they tend to be much more isolated, and we take advantage of the fact that the entrainment is much smaller as a kind of net response, as a net feature of the cloud. So that's two ways of, essentially it's the same thing, shallow goes to deep. Obviously, if you've given enough time and enough instability, but they're often treated separately. And so there's a little discontinuity there. And in terms of the actual schemes in the model, this is an earlier version. So basically, this takes advantage of the fact that there's convective inhibition. So that's when air parcels, sometimes from the turbulent kinetic energy in the atmosphere, are able to traverse this area of stability. So sometimes, nothing, it's just pure turbulence, and then when it is able to traverse that area of convective inhibition, shallow cumulus forms. Kind of a little bit differently on the deep scheme, there's this quantity called convective available potential energy, CAPE, and that's always used as a metric for how strong will convection be. And basically, it's an integrated buoyancy measure. So you calculate the buoyancy, and then the strength of CAPE, which is the blue area essentially, is used to determine the cloud top and the strength. So again, slightly different formulations there. The next piece is cloud microphysics. So when I talk about cloud microphysics, it's when condensation occurs, either liquid or ice in clouds. And so the kind of dynamics of the condensation formation is obviously much tinier scales than the kind of larger scale. And so many important aspects, not just the mean kind of condensation that results in the clouds, but also aspects of the size of the particles is really important, and for ice, the shape of the particles. And then the precipitation, the phase conversion back and forth from evaporation, condensation, and the sedimentation of the particles is all determined by the cloud microphysics. And two things that really come out in terms of the kind of more large-scale use of the model and the important processes that are challenging is the interaction of microphysics with aerosols and the fact that they activate particles in the cloud, but the cloud microphysics also essentially rains out aspects of the aerosols. This is a complex, obviously, push and pull. And then the impact that has on radiation is fundamental to the way the model operates from an energetic point of view. Yeah, and this is a theme in terms of this kind of disconnects the processes in reality, shallow convection to deep convection, is one thing. It's just a matter of time between one and the other. But there's certain separations. And again, also, this is something in the model we would like to improve on, is the fact that the complex microphysics I'm about to show you is not used in the convection, either the shallow or deep convection. So that's it's very simplified, and so it's something we need to change. I can throw this at you, but essentially, this is just a wiring diagram to illustrate, the orange here are the prognostic variables we keep track of, humidity, water, the number concentration. So given a certain mass of, 1 gram per kilogram of water, there are a certain number of particles associated with that. And we predict that for snow falling out, rain falling out, and both for ice, liquid, and water vapor. And just to reiterate again, this then, is this intimate relationship to the aerosols and radiation. Where a lot of work is done, in relation to cloud aerosol feedbacks and cloud feedback sensitivities as well. So this is the crux of the problems we have to deal with, and similarly for ice there. And you can, at least I do. I'm not a microphysics person, but you can kind of water it down, narrow it down to say, it's autoconversion, so how particles fall out the cloud essentially, and accretion, if they're falling through cloud, how they collect water. That's the order 0 of cloud. So the next thing is radiation. So I'm sure people have seen diagrams like this before. So essentially, what we're showing here is a broad estimate of the global radiation budget. I think orange is shortwave, so solar radiation. The various branches are, absorption, reflection, surface from clouds. And similarly from the long wave, the broader arms are, absorption, re-emission back out to space. So, this is a very, very complex, budget of many, many different factors. It's often hundreds of watts. But, in reality, when you add that all together, in observations at least, you get a net absorb of 1 watt, and that's 1 out of hundreds. So you can imagine that, and that 1 watt is important because that's the total energy input, additional energy input because global warming, greenhouse gases over the 20th century, approximately. And so, it's important. You then realize how important radiation is, and so. So to keep that in mind in terms of how the model deals with the absorption and reflection related to radiation, both in the long wave and the short wave, up here is a kind of a nice diagram of the it's kind of simplified, but essentially it shows you the spectra of radiation coming from the sun. There's the visible there, and you get like ultraviolet and some infrared. And then the emission there, again, somewhat simplified, is at a lower power and essentially a lower temperature as well back to the Earth. So it's not as simple as that. In reality, on the left-hand side here, maybe a point. Here we have, just a repetition of this is the region of visible. And then these are different greenhouse gases, the major kind of three or four greenhouse gases. And bottom to top, and each one is the absorption. So these are the patterns that the radiation has to capture. It is really quite complex with these individual greenhouse gas contributions, water vapor as well. And the critical thing that we have to think about is there's this region called the atmospheric window, and you'll see 8 to 10 micrometers it emits pretty effectively. So essentially the Earth is cooling in this window, and if you plug up that window with additional greenhouse gases, which we are doing, then you're going to reduce that emission to space. So that's essentially the greenhouse gas. It's direct with the kind of traditional gases, carbon dioxide, water vapor, ozone, etc. But with water vapor, it's obviously the feedback. Critical thing is the feedback, and how will that contract the atmospheric window? So that's your water vapor feedback, essentially visually shown here. Just not to say much about radiation. If you're unfamiliar with calculating radiation, it has traditionally been a very expensive process to calculate. And a lot of it is to do with there are very fine absorption bands. You saw that previously, and you can kind of see that top value there. It's called a line-by-line calculation, so a very fine spectral calculation of the emission absorption properties of water here. And so that we just cannot afford to do that in the model in a reasonable amount of time. It's too computationally costly. One approximation that we do in this RRTM, the rapid radiative transfer model, is that you kind of stagger this methodology called correlated K distribution band model. And essentially, enables you to kind of order the most important bands in terms of absorption. And so that makes it much cheaper and less accurate, of course, but good enough. So this is my squeezing my 3-hour talk into 30 minutes. And so there are a number of additional processes that need to be parameterized. Of course, the boundary layer, and traditionally it's been related to Richardson number-based stability properties in terms of determining how deep the boundary is, how well mixed it is. In CAM5, which is the previous version of the model, it's in some sense, it's a nice extension of that shallow parameterization I showed in terms of the turbulent kinetic energy is associated both with mixing in the deep convection and mixing in the boundary layer and mixing in the shallow convection. But CAM6 is a different scheme than the one that you'll be working with this afternoon. I'll say a little bit more. I kind of deferred the discussion of that to pretty much the end. A couple of other things, gravity wave depth drag. So in this context, it essentially means if there's a flow over mountainous regions and the mountains are favorable to a maximum response in terms of vertically propagating gravity waves. And then, example on the right, there's a ridge orientation template. So essentially, for a specific orientation, if the wind is blowing over it and it's optimal, then you'll get strong gravity wave propagation vertically if the stability is favorable to that. In general, this is not important is not as important for the troposphere. Its greatest impacts where these gravity waves break in the stratosphere and can have pretty strong impacts. That'll come, I think, with a Wacom presentation probably tomorrow, I'm guessing, which is the height-up version of the model. Second thing is, beyond just having a standard surface stress, so a surface kind of form drag, there's also processes related to turbulent mountain stress. And so essentially, in a similar way, but more local, it's stability-based, and there's a kind of little kind of figure here. So, in certain stable regions, stable in the atmosphere, there's flow around the orography, but when it's unstable and it tends to flow over, the drag is different. And that's important, obviously, in orographic regions. One thing to note about gravity wave and turbulent mountain stress is it's kind of more difficult to parameterize than thermodynamic impacts because conservation of momentum is kind of a little bit more hard to exploit than conservation of water, obviously, and conservation of thermodynamic properties. So, 23. When you throw that all in, this is, again, I'm referring back to a previous version of the model. This is kind of explains everything we've talked about in terms of the individual schemes, and it's my, childish, cartoonish view of putting everything together in the particular schemes, and with the interactions amongst them. So definitely, I had a wiring diagram that's at the end of the presentation that kind of shows this more kind of less conceptually and more accurately in terms of how the processes relate to each other. Anyway, that's just to contrast that with now what are we doing? Now I'm going to move on and say CAM6 is very much different, and what has happened, details kind of don't matter, but the gross thing that's happened is instead of having a separate PBL, stratocumulus, SCU there, large-scale cloud, cumulus, in these individual schemes, now we've tried to be much more consistent in terms of continuity. I talked about, deep is really shallow, but later on. And we've tried to, put in a framework that kind of conceptualizes that, but kind of follows that model in terms of not having this disjointed shallow, different approximations to deep, different approximations. And so that's something called club. Oh, wait, sorry. So just to put that in context, as I described this more continuous parameterization of moist turbulence, what are we trying to do? And so back to these two pictures essentially, and so, even though we said, oh, we just have to represent a single value there and try and understand the mean impacts of mean relative humidity, does that give you the right response to this cloud field? Now we're looking to, can we look at continuous variability of the water, temperature, momentum, cloud water, et cetera, in that box? Can we describe that in a rigorous kind of way that we can parameterize? And so what we do is this kind of scheme that extends across all this moist turbulence called the cloud layers unified by binormals. So cloud layers is multiple cloud layers. Binormals is the approximation that is used for the distribution. So it's a simple Gaussian. It's actually two simple Gaussians. And this, just to reiterate, it unifies moist and dry turbulence, except deconvection. So it does not, just go back on what I said to start off with. It does not do deconvection. It can, but we haven't employed it to do that yet. And again, it's this seamless representation of moist turbulence. Is it cloudy? Is it raining? It's agnostic to whether it's shallow cumulus or whether it's stratiform cloud. And it also, the nice aspect as well, as I talked about, the microphysics is not in the convection. It enables the microphysics to now be used across more cloud types. Some details here essentially are saying that to do that you need higher order closures, which is basically the mean that is calculated needs to be closed by variances and covariances. The variances and covariances need to be closed by essentially skewness. There's one skewness of vertical velocity enables you to calculate predict these variances, covariances. Yeah, we'll go through it. So as just to visualize this is like the complex math, and it's not complex math, but I hate dwelling on this. But essentially, this is how it works. Now instead of predicting like theta L, which is liquid water potential temperature, some quantity, we're predicting, not just diagnosing, but predicting the vertical transport of that quantity. And so it's a vertical heat flux essentially. And then you can all these equations are required to close that budget. To essentially know everything about we don't know everything, but it's an approximation. But essentially the nice thing is you can quantify it in terms of, it's a vertical advection of that flux. It's turbulent transport, upward by the turbulence. Buoyancy production, so it's the stability, instability it produced. Dissipation, that makes sense. You're kind of, you get rid of you're reducing the vertical heat flux. And then there's a lot of kind of, the devil's in the detail of these ones, but related to the pressure fields, the subgrid scale pressure fields is a lot of terms. This is more visual, I think. I hope it will, I don't want to walk across, but essentially, again, this is like, for example, a thermodynamic variable here, a vertical velocity on the right-hand side, on the bottom. And so you can imagine these swirls here as a 2D PDF, 2D Gaussian, in the top to bottom way and the bottom left to right way. And that's, it's an ascending region, and it has, a particular temperature. So this is temperature versus vertical velocity. And so those blue regions are like, okay, there's a kind of well spread out, generally low vertical velocity of a particular warmish temperature. And if you look at now at the liquid water versus the temperature, this black line is saturation. So now you can map this particular simple, admittedly simple distribution to the fact whether it's clear or cloudy. So this region that lies over here is cloudy, and this is clear. So that is, it's just to emphasize, it's this continuous moist turbulence, not just a dry turbulence, not just the kind of cloud, liquid ice formation, well, not ice, but liquid formation. It's the continuous movement between the two. So that's where we are now in terms of club, and there's a lot of work going on for the next version of the model to kind of move this forward. 3 slides. I just want to emphasize again, this is a super old figure, but I really like it. Why are we focusing on, clouds, microphysics, particle sizes, aerosols, radiation? What says that? Of course, they're important processes, but why? What really, doubly, why should we focus on that? And this is kind of motivation. It's basically saying, what happens in clouds when we double CO2? It's CMIT3. I mean, I'm sure some of which is, probably 10, 15 years old. But basically, this says, what is the change in low cloud amount? So what's the sensitivity of cloud? And of course, that impacts radiation. And in the GFDL model, the cloud disappears in some of these key regions with stratocumulus, the deepest blue, the deepest purple. Of course, the cloud disappears, global warming, you're not responding to global warming. You make it way easy for the solar radiation to hit the Earth. So, plus 4.2 climate sensitivity to this. Whereas NCAR model, cloud increases. The processes we have in there and the increase in CO2 leads to cloud increasing. So it's just to emphasize that's why we focus on these things. This is why the model is used, not the only reason, but it's the gross reason, is climate sensitivity, essentially. So I just have one future parameterizations. I've described everything that we've kind of done and are doing right now, and where do these extensions and improvements lie in the future? As we go to higher resolution, microphysics really does play a greater and greater role in how the model responds, particularly in terms of precipitation processes, and extreme events in the future. And the microphysics we have right now is relatively simple still, but so there are a lot of kind of untapped processes that we need to represent ice production. There's a million different types of ice production, for example, and we need to investigate that. This here is the club extension, so mass flux being like deep convection. So we're here, and we want to extend to here. That makes a lot of sense. There are various ways of approximating the way we represent physical processes within a grid box. This is called super parameterization, and the bottom line is we can put a simple cloud resolving model. It's expensive, but it does represent a lot of key organization type processes. This is how we're doing high resolution, essentially, which is instead of doing 10 kilometer high resolution globally everywhere all the time, we're doing a lot of these focus type experimental setups. Example here in West Pacific and off the coast, of the US, to kind of represent atmospheric rivers or the Madden-June oscillation. So that's really taking off now. A lot of people are using that. And also, a piece of what we do may make sense to replace some of the, the prognose of processes I've described with machine learning techniques and emulators. And, I think people are aware you can do a very good job now of emulating some of the processes and, representing, the behaviors, much more cheaply and much more faithfully when it's trained on the right data. So I have one summary. That's it. I'll just leave it up. Yeah, because I'm running out of time.
All right. Thank you, Rich. It's time for questions.
Losing my voice.
All right, questions. This side of the room has been very quiet. I'll be looking there.
Thank you for the very nice talk. I have a question about the Chem6 club. So in the morning, Peter talks about the coupling strategies like a process split and time split. Seems like for club, you are choosing the process split instead of a time split. But I'm wondering, like, when you add all the PBL, large-scale cloud, or those process actually have different time scales. If
They
you
do, I mean, they do locally. I can never remember the route. So we do, I think it's time split generally. But for club, we process split it with the microphysics. It's unfortunate, it's on one of my other slides, but instead of saying process, tendency, update state, process, tendency, update state in a very linear sense, once you get to where we do club, there's a kind of sub-cycling between club and the microphysics.
oh, okay.
Because the microphysics processes are so fast that if you give it strong, significant tendencies, you do things like rain everything out, or before the feedback can occur that would come from the turbulence of club. So we have experimented with this. There is sensitivity to this, yeah. But basically, yeah, they're in parallel essentially on a subloop that I think it's six. We loop it 6 times, I do believe. No, we loop. I can't quite remember the detail. I think we do club 6 times and then the microphysics 3 times. I can't quite remember.
Just clarify, what you said is like even they are in the same equation, actually, for each process or each term, they have the cycles, subloops.
Yes, I mean yeah. I mean, you're talking about club specific on its own, or you're talking about with respect to the microphysics?
I guess is for the I think there is the equation you mentioned, like
This is microphysics. Are you talking about that equation I complained about? Yeah.
oh, yeah, this one.
This one, yeah. That's just club, all club. And then you determine the tendencies, you move the model forward, and then you have a state that the microphysics can act on.
Oh, okay.
So it's external to the core club, but they are in parallel essentially, so that we don't get like too excessive tendencies from microphysics.
Thank you.
Yeah. My question is in line to that. So this parameterization uses the K theory, diffusivity. This theory has been in the literature a long time ago. Now,
in momentum?
Huh?
Are you talking about in momentum? Or?
Yeah, the momentum and heat and moisture as well. So
well, it's diagnosed. The diffusivity is diagnosed in the momentum, but it's not in the temperature and humidity.
Okay, now, but my question is now, are there any means in the future that with the advance in the computer resource that we have, running like eddy simulation and learning something about those?
Oh, I mean, yeah, there's a whole field. You know, a lot of this is derived from large eddy simulation, cloud resolving.
Integrate them into the global model?
Yeah, I mean, so a lot of that comes from knowledge about the role, the balance between the different terms. Is dissipation larger than buoyancy production, and so and a lot of knowledge comes from comparison of LES.
Okay.
And what explicitly, you can explicitly resolve the budget in LES to say, okay, dissipation is way too large in the model, and so we need to modify that.
Yeah, thank you.
Okay, I think that was the question.
Go ahead. Because the physics parameterizations are calibrated at certain scales. So then when we're using like a variable resolution model, is there any are there different parameterizations? Is it the same one, or how does that work? Is it appropriate at all those scales?
No, that's a great question. That was one of my. I'm gonna cheat. Is it here? So essentially, I can't quite find it. Essentially, right. I mean, this is just one figure, and so essentially here, this is an example of same convection, cloud fraction. What does it look like if we do 2 degree, 1 degree, half degree, quarter degree? And you're right. It's inappropriate if you believe that these, these heating rates, for example, are not correct. That being said, something like deep convection, if you do go to small scales, you would expect to play a lower role anyway, because the kind of asymptotic cases, you resolve the storm from 100 kilometers. So you imagine at some point through that scale, the need for deep convection, and that's true in many weather models, goes away because you're at kilometer scales. The question is should such a sensitivity occur with a halving of the resolution? Probably not, I don't think. So people probably hear scale-aware parameterizations. There are methodologies for, and scale-aware means, the parameterization knows its real scale. I'm a deconvection, I know my scale, and this is the way to kind of calculate that and keep it appropriate as the grid scale gets finer and finer. So, just circling back around to your very original point is, yeah, we do use this in these regional refine, and we do not, in general, make changes. Yep.
I just have a silly question about the.
No silly question.
What's the meaning?
My silly answer. That's it.
What's the meaning of the subgrid for the CAM6? Because I know the subgrid for CIM5. It means in a grid cell, it has like different plant function type, such as this
Right.
kind of thing.
It's a little bit
But
different. Oh, sorry.
Yeah, but for the CAM6, what it is and how to achieve it.
Right. I think for CLM, it's much more explicit thing in terms of, you're talking about the plant function types and the tiling in CLM, because they have subgrid scale. It's like, let's say there's a 100 kilometer grid scale, which is general, it's the same as the atmosphere. 20% is urban, 50% is lake, 20% is C3 grasses. I mean, is that when you say subgrid, are you referring to that from the? Well, it's a much more amorphous concept in the atmosphere. And we're talking about, the pictures I showed with the 100 kilometer grid box. I mean, it's hard to define exactly what I mean by subgrid scale. If it's cumulus clouds, that has a different kind of characteristic to one deep convective cloud. So it's not quite the same as somewhat static concept in CLM where, like I say, these tiling types are somewhat static in time for the most part.
But how to get the calculation for the subgrid scale?
It depends where Club assumes it's a Gaussian. I mean, there's no particular geographic location that Club thinks something exists. Mm-hmm. It just thinks, given a mean and a standard deviation, it's a Gaussian statistical distribution in the grid box. It's not an explicit location. It could be, and we're working on that actually. It could be, yeah.
Thank you.
Okay, thank you very much for this great presentation. So my question mainly related to, do you have a recent research mainly related to the parameterization, how this could improve the prediction of this model over this location or this location, especially the interaction between the ocean and the atmosphere?
Yeah, that's a big question. I don't think I think our, research, parameterization, just model research, it tends to be more general than saying we want to improve, especially to a particular region. Sometimes it is the case, and I can say, just now remembering, we have someone, Patrick Callahan, working on flow over strong orography, the Andes, for example.
Yeah.
And there was he's done quite a bit of nice work about the accurate pressure term representation there that is really, essentially we have problems with precipitation sits on top of topography, not just the Andes, in many places. And he really targeted that. But I would say that's an exception rather than the rule. We're more general. Club is a good thing to do. It's more statistically robust rather than, I think it will necessarily fix this geographic problem. Yeah.
Yeah, I think also the main issue for me is mainly related to the impacts of the stored energy inside in the ocean and the atmosphere itself. So because of the energy budget,
okay.
How this could affect.
Yeah, I mean, I go back to that residual number of 0.9 against the backdrop of, hundreds of watts. And it is, that's where sausage making, whatever you want, comes in, where it's, we think we're doing the right thing with all those components, the energy flux out of the ocean, et cetera, and we can put the model together and we could be 20 watts off. Mm-hmm. So it's, this is the devil in the detail of climate modeling that is different for weather forecasting is energy residual really matters, and it is really hard to get in a what's the word, in a in a way that is pure, as in like we made all these changes, it's great, and look, it's 0.9 watts out. That never happens.
Understand.
Yeah.
Yes. Okay. Thank you.
You spoke of shallow clouds over the ocean. So in some models they simulate too much shallow clouds over the ocean. That is a problem. But we have also seen that over the land, especially in the tropical region, if the model is unable to simulate the shallow cumulus, then certain times the deep convective systems are not simulated at the right time, and also the intensity is not simulated. So I think this is somewhat related to the way the boundary layer turbulent processes are represented. So can there be different representation of such feedback processes for the ocean and the land? What is your opinion on that?
I mean, I wouldn't like to say there's different representation of processes over land. I would hope there are different representations of sensitivities that are inherent to the scheme. You know, I do a little bit of like downward cycle precip, and it's a very persistent common problem is this early precipitation max. You know, in most places over the land, it's maybe 6 p.m. or something, but oftentimes it's closer to midday, and this is a very challenging problem because it does involve this surface fluxes, you know, building of the boundary layer, shallow, you know, and then deep, and it's very, it's just over land it's a very hard problem. Over ocean it's still a hard problem because, you know, it relates to cloud top cooling of deep convection can set the time scale, and less of a problem, but it's still a challenge.
Hi. So in some of the earlier figure you saw like cloud cover versus relative humidity, like still we are using that same parameterization in the.
We are not, but there are many representations that do, because it's you know, for climate models it's probably not used that much, but for forecast models, you know, it may well be. I mean, it's simple approximation. Like I said, the radiation. I didn't say this, but like in forecast models, it's nothing to do with radiation. They don't. All the radiation things I said, they kind of don't care so much more now than they did like 10 years ago. And so I think it's less of a problem for them. And I may be wrong. I'm not too familiar with like WRF parameterizations, for example. But I'm pretty much guaranteed some forecast models around. Some uses of WRF do a simple cloud fraction parameterization like that. Yeah. Okay. I mean, I know that European Center, they predict cloud fraction, which is a strange thing to predict.
Yeah, because in 50% relative humidity, you are still getting some cloud. So that is
right.
So
and that figure I showed is like that. I mean, that's regime specific. Yeah, I mean, you could imagine, you know, in a stratiform type situation, as soon as you get cloud forming, a little bit more relative humidity, it forms everywhere because it's pretty homogeneous, the response. But something like deep convection, nothing happens, boom.
Yeah, thanks.
Okay.
All right. Thank you so much, Rich.
Yeah, no worries. Thanks
really
all.
Appreciate it.
Good luck.
Oh, and you can check the Meta Scientist sign up. Rich is having lunch with some people, and there may be spots available if you wanted to meet with him if you don't already have a person. Okay. I'm just going to hold this up. So we're doing kind of a check-in right now about the lab exercises. So most of the rest of the afternoon is going to be lab exercises. And what we wanted to check in about, we're going to use the same website, the same account. We should have a queue this afternoon because we thought more people would be actually building and running the model. So that should hopefully enable getting through the queues quicker. What I wanted to check with people, so the goal today was to kind of get through this for the whole day, was to get through the basics. How many people have started the exercises already? Can you just raise your hand? Okay, so a number of people have started. How many people are still working on downloading the code? Okay, and if you feel like you're behind, don't worry. A lot of people had account issues, so you shouldn't feel embarrassed or anything. Okay, so people who are working on downloading the code, I'm gonna have you go to the Chapman room. So I'm gonna try to show you on this map. So we're gonna go up the stairs. Instead of going to the library in the Damon room, let's go to the Chapman room here. So that's like down the hall and then just off to the left, and we'll I'll assign one of the helpers there. I don't know that all the helpers are here yet. And then if you have already successfully built the model, why don't you go ahead and go to the daemon room? And if you're still kind of working on, the QCMD case.build, that situation, go to the library, okay? Does that sound good? Does anyone have any questions first? We got one over there. Go ahead and just say it since this is like a in the room logistics. Guys, don't get up yet because I won't be able to hear him. Okay. Okay, so the question was about documentation on comp sets. Here, if you go into the create a new case with the setups, there's a whole bunch here about case naming conventions, resolution, and then comp sets. And if you click right here, it'll show you what the CESM2 supported comp sets are. I want to emphasize we have anticipated that you will read through this workflow. And then once you've read through it, that's the information about how to set up your cases. Then you have the information to do the exercise. Instead of making you sit here through a lecture where we tell you, this is how you create a new case. Here's what what all this means. And you look at this and you go, oh my God, I will not remember that. So we're anticipating you will work at your own speed, and we know people will work at different speeds, and that's okay. But yeah, today the goal was kind of to get your first case built and run, and then tomorrow we'll be able to make modifications to that. The other thing I wanted to just point out, so we'll come back here at 4:30 to just kind of do a check-in, see if there are any overarching questions that we should answer. When you leave this room, check for your belongings. I saw a couple water bottles in here at lunch when I came through. And if you have trash, please take it out and throw it away outside. Okay. So people who are still working on downloading the model, go to the Chapman room. If you've already built a case, go to the daemon room. Helpers, will you come up here?